All right, well, we've looked at charges, we've looked how they've reacted, how to charge things, how to take away charge, how to ground, and now it leads us to our next thing, which is Coulombs Law and how to mathematically equate some of this. So, first off, to review what we just previously talked about, force is a vector quantity, okay? So, when we look at this repulsion forces here between these two objects, these two forces are equal but opposite, right? If the repulsion are going opposite directions, so this would be a force and this would be a negative force. If the force is attractive, this case, an object D, it's going this way, so it's going in the negative direction, and this one will be going in the positive direction. But again, equal and opposite, same forces, opposite direction. So the charges will be different, but the magnitude will be the same. But they are vectors. Coulombs Law equation, very similar to the gravitational equation, and we'll get to how those compare in a little bit. But what we want to see is, right here, we know that if we define the force of electrical attraction, we need to know the charge of the two objects in coulombs, the distance that they are separated in meters, and then you have this constant here, constant K, and you can see it's a pretty large constant. It's 9 times 10 to the 9th, really big number. But it's newtons times meter squared per coulomb squared. Now why that's important is that the meters get squared, so that cancels out meter squared, coulomb squared, cancels out coulomb squared, and so our force will be measured in newtons, just like we want it to be. So the charges of the two items multiplied by each other, multiplied by the constant, divided by the distance in meters between them squared, will find us our force. Let's do some samples. Suppose we have 2-point charges, each with a charge of 1 coulomb, are separated by a distance of 1 meter. What's the electrical force of repulsion between them? So first things first, we draw a little picture. This has a charge of 1 coulomb, and this one has a charge of 1 coulomb, and our distance between them is 1 meter. Once we know that, we know everything we need to know to find force, because our force is K times the charge of one times the charge of the other over the distance squared. So K, as we previously said, is 9 times 10 to the 9th. Our charge is 1 coulomb for here. Our charge for here is also 1 coulomb. And we divide that by our distance, which is 1 meter squared. So a lot of ones here, but our answer is 9 times 10 to the 9th newtons. So that is the force, okay, of these two positive charges. So this would be a force of repulsion. This one would go 9 times 10 to the 9th this way. This one would go 9 times 10 to the 9th that way. That's a really big force. A coulomb is a huge amount of charge. Huge amount. Here's one that's a little more realistic when we talk about it, and it uses nanocoulombs. And this is something we want to address here in a second. But two balloons are charged identical quantity and type of charge, negative 6.25 nanocoulombs. They're held apart at a separation of 61.7 centimeters. We want to find the magnitude of the force of repulsion between them, both negative charge. So here's balloon 1, okay, with negative 6.25 nanocoulombs. We have another balloon with negative 6.25 nanocoulombs. And our distance is 61.7 centimeters between them, okay? We got our charges, we have this now. Remember, in the equation, we want things to be coulombs, okay? So when we look at nanocoulombs, a nanocoulomb, or 1 coulomb, is equal to 10 to the 9th nanocoulombs. So all we have to do to make this conversion, and this is probably how you'll see things mostly is in nanocoulombs, is we just got to times it by 10 to the 9th. So this is negative 6.25 times 10 to the 9th coulombs. And this is negative 6.25 times 10 to the 9th coulombs. So anytime we want to go from nanocoulombs to coulombs, multiply by 10 to the 9th. Another charge that may come up is microcoulombs. That's 10 to the 6th microcoulombs. Alright? But the math, again, just take it times 10 to the 6th if it's microcoulombs. So now we have our charge in coulombs. The other thing we want to look at is our distance. Our distance needs to be in meters. Go from meters to centimeters, move the decimal to the left. 0.617 meters. So we have our distance in meters and our charges. Now we just pop it into our equation. K times Q1 times Q2 all over distance squared. K 9 times 10 to the 9th. Multiply by our charges, negative 6.25 times 10 to the 9th. And we're going to square that because they're both negative 6.25 times 10 to the 9th. And we're going to divide by our distance squared, 0.617, the whole thing squared. You punch all these numbers in your calculator, and what you should get is a charge or a force of 9.23 times 10 to the negative 7 newtons. This is a really small force, and this is what we expect with really small charges. Nanocoulombs, small force. So that means that this object, this balloon, is going 9.23 times 10 to the negative 7 newtons to the right, and this object's going to the left with the same. One of them's going to be negative because it's going to be a vector. I would make this one negative, this going left, but it doesn't matter. One's negative, one's positive when we talk about forces, even though both charges are negative. Let's look at one more example with force of attraction and how we can use this equation to solve for other things. So we have two balloons. One has a positive 3.37 nano or microcoulomb charge. The other has a negative 8.21 microcoulomb charge. So there's your microcoulombs that we previously discussed. They attract each other with a force of 0.0626 newtons. So it's a relatively large force. We want to find the separation distance between the two balloons. All right, so again, draw a picture. This balloon through positive 3.37 microcoulombs. This balloon's negative 8.21 microcoulombs. Since they're opposite charges, the forces are going to attract, so that's what we're going to see with our forces. We got to take microcoulombs and convert it to coulombs. 1 coulomb is 10 to the 6th microcoulombs. So to make this my microcoulombs into coulombs, I just multiply by 10 to the 6th. So 3.37 times 10 to the 6 coulombs, and negative 8.21 times 10 to the 6 coulombs. So again, convert to coulombs. Our distance we don't know, but we know our force is here. So let's look at our problem here. We got force is equal to K times Q1 times Q2 over distance squared. I'm going to solve for distance. So the way to do that, again, a lot of ways. We'll just punch numbers into our equation. We know our force is 0.0626. That's equal to our positive charge of 3.37 times 10 to the 6 coulombs, multiplied by negative 8.21 times 10 to the 6th coulombs, multiplied by our constant, 9 times 10 to the 9th. All right? Where the coulombs will cancel out of it, and then we want to find d squared. I'm not going to bore you with the algebra with this. If you want to check my work, you can, but I would go through the algebra to make sure you can do this. But in the end, as you solve, you're going to find out that your distance is going to be 1.99 meters. Which is what we expect to see. Now, remember the two equations. This is gravity. This is electrical force. Both have a constant. Here we're taking charges and multiplying. Here we're taking masses and multiplying, but distance squared is still a part of it. Very similar equations. Here's what's different, is that electrical constant is really, really high. Gravitational constant, really, really low. But when we talk about these forces are still forces, but you can see how they work together and how they compare. And this inverse square relationship that we talk about with gravity will come back to electrical, and we'll get to that in the next video. So, force is 1 over distance squared. Two charged objects have a repulsive force of 0.080 newtons. If the distance is doubled, then what is the new force? If you recall from gravity, okay, we have this. If our distance is doubled, they get farther apart. So 2 squared gives me 4, which means I have to take this and divide by 4. And when I do that, I get 0.020 newtons as the new force. So remember the inverse squared law when we did those before, and there'll be some on the assignment that you'll see this.